So as we move forward here with lesson 20, I want to introduce a new concept today. We're going to revisit it on Monday as well. Do some more work with it Monday. But this is a concept that if you're not paying attention carefully, you're going to get really, really lost. All right, so please make sure that you are paying close attention here. But again, if you aren't paying attention here, you will get lost on this. Okay, so just really try to focus and follow here. Okay, so we have these derivatives that we've been able to find. Okay, here just as a little warm up, remember here we have the chain inside a chain. Okay, because the square is on the outside, so y prime is going to be 8 sine to the first of 5x times the derivative of sine, which is cosine of 5x, times the derivative of 5x, so times 5. So the whole thing would be 40 sine times cosine, okay? 40 sine of 5x times cosine of 5x. All right, and then over here, this is kind of getting into what we want to do today. How would we handle a problem like this? Okay, we would divide this by x, so it's now y equals 6 over x, or 6x to the negative 1. So if I'm finding if f of x equals y, then f prime of x would equal what? Negative 6x to the negative 2, okay? Or negative 6 over x squared. Okay? So that's something that you've done before, but I haven't given you anywhere it wasn't already solved for y. Okay? Now, at this point, we could go ahead and evaluate. If it's f prime of 2, what's our answer? Yeah, negative 6 over 4, which is negative 3 halves. Okay? But what we see here is the difference between what we call an explicitly defined function and an implicitly defined function. Okay? Here, this xy equals 6 is what we call an implicitly defined function. Y is a function of x, but it's not solved for y. It's implicit. Okay? Explicitly defined would be when it's already solved for y. Y is 6 over x. All right? We have a couple of examples here. Similar, the similar idea here. We have xy equals 1 implicitly. Explicitly, it'd be y is 1 over x, or x to the negative 1. And then we can take the derivative. Taking the derivative when it's explicitly defined is what we've been doing the whole time so far. Okay? The challenge with this is the fact that you cannot always write a function explicitly. Okay? Now, we already showed that for xy equals 6, you can. All right? But I want to actually introduce this whole concept of finding the derivative implicitly using an example we already know how to do explicitly. And then we should be able to see that the answer will end up being the same. Okay? So, one thing to remember is throughout this whole process, no matter what variable we are taking the derivative of, we are going to be differentiating with respect to x. This is where that dy dx really matters. Okay, that kind of notation there. So, if I'm going to find the derivative of xy equals 6 implicitly, the first thing I'm going to do is differentiate both sides of the equation. Okay? Do the derivative with respect to x of both sides. Okay? So, I'm taking the derivative with respect to x of the product xy. Okay? And I'm taking the derivative with respect to x of the constant 6. Alright, so what does the right side equal? 0. Derivative of a constant, 0. On the left-hand side, how would I have to do that? Product rule. This is a product, okay? So, I'm taking the derivative of the first factor. So what's the derivative of x? 1 times the second factor, y, plus the first factor, x, times the derivative of y. How do we write the derivative of y with respect to x? What?
dy dx.
dy dx. Okay? It's dy dx. Okay? Now, that's what we're trying to find, isn't it?
Yeah.
Okay?
Doesn't it just mean derivative always?
Yeah. That's the derivative of y with respect to x. So guess what? We can now use algebra to solve for that. X times dy dx equals negative y. So dy dx is negative y over x. Okay? And that is our f prime of x. Well, let's go ahead and test. Let's go ahead and test. Did we get the same thing we got when it was done explicitly? All right?
6 over x and 6x negative 1.
Okay, so here, if I'm thinking about this explicitly, y is 6 divided by x. So, if I have a negative 6 over x, what does that equal? Negative 6 over, not 2x, x squared.
Why don't you do 6x and negative first?
You could.
And then, oh, okay, yeah.
Yeah.
I don't know, I just didn't.
Either way, it'll come out. And guys, that's what we got up here when we did it explicitly, negative 6 over x squared. So it is the same thing. It's going to give us the same value. The difference is we just found it implicitly. Okay? Now, I already said that f prime of 2 ended up being a negative 3/2. Okay? Well, f prime of 2, if I'm doing that implicitly,
One would negative y over 2.
it's going to be negative y over 2. So I need what the y coordinate is when x is 2. Alright, so think back to our equation. I have 2 times y equals 6.
So then wouldn't the y prime be negative?
2 times y equals 6. So that means y is 3. So the point that I'm really finding the derivative at is the point 2, 3. Okay, so here's, guys, I was telling you before, back when we first started finding the derivative at a point, yes, right now we're just plugging x in. But now that we have implicitly defined derivatives, you may have to plug in the x and the y coordinate of the point, like we do here, and we end up getting a negative y over x, so negative 3 over 2. Okay? Let's look at this example down here, okay? If I have the derivative with respect to x of y cubed, where y is some implicitly defined function, okay? I need to take the derivative with respect to y of y cubed times dy dx. What am I using here? Chain rule. Chain rule. I have a function y inside of something cubed. Well, what's the derivative of something cubed? It's 3 times that something squared. Okay? And then I need to use the chain rule to multiply it by the derivative of the something. In this case, the something is just a y. So what's the derivative of y? It's dy dx. Okay? Same idea with b. What's the derivative of x? 1. What's the derivative of 3 times something?
3 dy dx.
3, but I need to multiply it by the derivative of that y, so 3 dy dx. Okay? Again, just take the derivative like you would if it were an x, but then multiply it by a dy dx. What would I have to use for c here? Product rule. Okay, so the derivative of x is 1 times y squared plus x times the derivative of y squared. 2y dy dx. Okay? The derivative of something squared is 2 times the something to the first, then times the derivative of the inside. The derivative of the y is dy dx.
So can you simplify that to be 2y third?
No, it's addition, so it would just be y squared plus 2xy times dy dx.
Is everything being multiplied by dy dx?
No, just the term that has the y in. So it's not, we're not multiplying this y squared up here. Or wait, yeah, we're not multiplying this y squared here. Because that was our f prime g. So you just write the function. We didn't actually take the derivative there.
Oh.
Okay.
Why is it not just dy dx squared?
What do you mean dy dx
Like
squared?
the derivative of the g of x when you're multiplying it by the x.
Oh, because of the chain rule. When I'm finding the derivative of y that's being squared, the outer function is the square. So I take the derivative of the outer function and it's 2 times that inner function to the first. But then I have to multiply by the derivative of the inner function, which is dy dx. Okay?
So it's like a chain rule and a product rule?
Yeah, in this case, yeah, we had chain rule and product rule here. Now, let's put these ideas together. I did this on the previous one. We've done a few of these here so far. But how do we find dy dx if we are given this equation? All right? So here's our process. And this is what you're going to do anytime you have one of these. Okay? First of all, you're going to find the derivative of both sides. So, over here I'm taking the derivative with respect to x. And over here, I'm taking the derivative with respect to x. Alright, so on the right-hand side I get 0. On the left-hand side, the derivative of something cubed is 3 something squared times the derivative of the inner function, so times dy dx. The derivative of something squared is 2 times something to the first times the derivative of the inner function. The derivative of a linear part is just the constant, so -5, but I need to multiply it by a dy dx. And then this x part I just do like normal, minus 2x. Okay? So at this point, we have first of all taken the derivative on both sides. Okay, the next thing that we're going to do is we're going to get all terms that have a dy dx on one side. And obviously then get everything else on the other side. Okay? So in this case, I'm going to add the 2x to both sides. And you'll notice now every term on the left-hand side has a dy dx.
You can factor it.
What'd you say?
You factor it out.
We can factor that out. Okay? Now that those all have a dy dx, we're going to factor out a dy dx, and what's left is a 3y squared plus 2y minus 5. Okay? So we're going to factor out and then finally we're going to simply divide. Okay? To get the dy dx by itself, dy dx is going to equal 2x divided by that 3y squared plus 2y minus 5. Alright? So that's the process. Anytime that you have to find dy dx for one of these functions, that's what you're going to do. Do the implicit differentiation and then isolate dy dx with your algebra. Okay, so here on the bottom you can kind of see that layout that I gave you. Those steps that I just gave you. Differentiate both sides with respect to x. Collect all the terms that have a dy dx on one side and all the other terms on the other side. Factor out a dy dx and then divide to finish solving. Okay? And that's really all there is to it. Don't overcomplicate it, but do be careful. Alright? Alright, let's try a couple other examples here. Okay? Example number 3. We can use implicit differentiation with parametric equations. Okay? We were just talking a little bit about parametric equations before we started, right? So here, remember, parametric equations are equations where we represent the x direction and the y direction, and z if we wanted to do three-dimensional ones, all in terms of a time, t. Okay? So what we're going to be finding here is we can find dx dt, and we can find dy dt. Okay? So I'm differentiating with respect to t in this case. Now both of these are written as explicit functions in terms of t. So would I have to do implicit differentiation here? No, I wouldn't have to in this case. My dx dt would be, and I can do this even with the plus or minus, it's going to be 1/2 t cubed plus t squared minus 5t plus 4 to the negative 1/2 times 3t squared plus 2t minus 5. Okay? And I can find dy dt is just what? 1. Okay? Just 1. So I can do that explicitly, alright? But I can also do some other things. I can do an implicit if I were to rewrite this function, okay? If y equals t, I could say that x is going to be plus or minus the square root of y cubed plus y squared minus 5y plus 4.
So here you're putting dx dy. Are you still writing it as dy
Okay.
dt?
Well, I can still, actually at this point, I can do dy dx. Alright? I can find dy dx. Alright? So, if I take the derivative of the left-hand side, I'm just getting 1, right? But on the right-hand side, I have plus or minus 1/2 square root, or not square root, y cubed plus y squared minus 5y plus 4 to the negative 1/2 times, and then here's the difference, here's the implicit part. It's going to be a 3y squared dy dx plus a 2y dy dx minus 5 dy dx. Okay? Does everyone see what I've done here? So at this point, I need to get the dy dx by itself. So I'm going to multiply both sides by the plus or minus half, or plus or minus 2. And I'm also going to bring that y cubed and so on to the negative 1/2 to the other side by multiplying to make it a positive exponent. Okay? So that's going to give me a plus or minus 2 radical y cubed plus y squared minus 5y plus 4. Okay, and that's going to equal the part that's left over, which all those parts have a dy dx in them. So I'm going to factor that out. You guys see what I've done there? I took all of this and I multiplied to get it over to this other side, and then these three terms all had the dy dx in them, so I factored it out. Okay?
So you got that positive exponent. You could have either divided by that and then you just brought it up, or what did you do? You multiply.
Well, it's over the square root of that, right? Because it's a negative 1/2 power. So if I multiply both sides by that, it'll make it a positive 1/2 power to get it to the other side.
Or you could just, if I didn't see that, could you just divide and then bring it up?
Yeah.
Okay.
All right. So there, at this point, now we know dy dx is going to be plus or minus 2 square root of y cubed plus y squared minus 5y plus 4 all over 3y squared plus 2y minus 5. Okay? Now notice what we have here. This y cubed plus y squared minus 5y plus 4 square rooted, that's what x is. So you remember we just did this similar one on the previous page. It's plus or minus 2x over 3y squared plus 2y minus 5. Okay? We actually ended up getting the same answer, even though this, in this case, the original function was written using parametrics. Okay? Because this right here is the x.
Doesn't matter if we write it with that x versus the whole parametric.
No, but I just wanted you guys to see that that's what ended up happening there.
Is that always gonna happen?
No, not necessarily. But in this case, I think it happened simply because y equaled t.
Yeah.
Now we're going to skip example 4. I always forget to take this out, but that's exactly the same thing that we just did on the previous page. Okay, that's the same example. Alright, so we're not going to do it again, but I will show you this. I do want to show you this. This is what that graph would actually look like. That's kind of cool, huh? It's not a function. Okay, but that's what that would look like. And really what we're doing here is we're getting to finding derivatives of things that are not actually functions. And by the way, that's why the derivative ends up having x's and y's in it, because x equals 1 isn't only going to give us 1 point. So the slope is not going to be the same here when x is 1 as it is over here when x is 1. It's actually a derivative that's dependent on both the x and y coordinates because we're not dealing with a function. Alright? But notice here, okay, we have different points, 2, 0. If we plug in 2, 0 into our derivative that we had, we'll get a negative 4/5. Alright? Which makes sense. If you look at it right here, you know, it's going downhill. Okay, so there's our derivative with the negative 4/5 going through 2, 0. At 1, negative 3, you can see the tangent line is going to be something like that. So you see a positive 1/8 slope. At x equals 0, it's 0, negative 3, or 0, negative 3 point something. But it's negative plus or minus 2x over something, right? So, since x is 0, the whole thing will equal 0. But then up here at 1, 1, notice we have a vertical tangent line. Our derivative ended up being undefined. Okay? So, that's how we could use that. And that, guys, is the process of finding dy dx implicitly. Okay?